Hello everybody, this is Dr. Christopher White, and in this brief presentation we're going to spend a couple of slides thinking about types of data that a geologist will collect. So a geologist will collect two types of data. There's qualitative data and quantitative data. And so we're going to think about these two different types of information and essentially what they mean, and we're going to think of a few examples. So let's start with qualitative data. So qualitative data are essentially descriptions. So we're conveying information in the form of words or sketches, but we're not actually giving any numerical data. So if we look at this picture here, what can we see? Well, we can instantly tell we're probably in some kind of volcanic environment. Now, what kind of things can we describe in this picture? Well, to start with, we could do a sketch and we could show how we have loose sediment down here in the foreground. We have this outcrop of rather smooth looking rock here, and we have this area of much rougher looking darker rock right here, which was probably a more recent lava flow. So we can do a sketch of the area. Then we can talk about, for instance, the colour of the rocks. As I said, we can talk about the textures of the rocks. This one's smooth, this one's rough. Then we can discuss things like the steam. We can say, right, is this hot steam or is this a relatively cool steam? And we can discuss things like the smell of the steam. Does it have a sulphurous smell to it, for instance? So all this information is qualitative because we are describing what we can see, or maybe we're even drawing what we can see, but we're not actually giving any kind of numerical value. So when I'm describing the steam that we can see here, I might say it's hot, but I'm not actually giving you a temperature in Fahrenheit or Celsius. Now, the other type of data we can therefore collect is quantitative data, and these are numeric measurements. And so this, examples, this would be things like height, for instance, the temperature of the steam. We may do analysis of the minerals in rocks. We may take the whole rock, powder it down and analyze what the bulk composition of a rock is, for instance. So this is data that comes with numbers attached to it. And of course, once you have this quantitative data, well, then you can compare it to other data from the same location, or you can compare it to other data from different locations. And so you can see that both of these types of data are distinct in what they can tell us, but they're both equally as valuable. So I know, in your head, you probably assume instantly that quantitative data is going to be the more valuable data because it's going to have the numerical values associated with it. But a lot of the data that a geologist will actually collect will be qualitative data. So we'll be describing the rock, we'll be describing the outcrop, we'll be describing the geology in a general area. That's where a lot of the information is going on. It's only later in the process where a geologist will actually start taking, numerical measurements of rocks, of their chemistry, of their minerals, etc. So although quantitative data on the face of it seems like the more important source of information, in geology a lot of the information you will actually collect and distribute will be qualitative. So we can't always assume that numbers are superior to descriptions, in the case of geology at least. So let's have a think about this situation. So now we're going to think about density versus weight. So if we look at this diagram here, we can see we have a body of water, and in this body of water we have three cubes. One cube is clearly made of wood, one cube is clearly made of water, and one cube is clearly made of stone. Now, from a qualitative point of view, we can make general descriptions, we can talk about the shape of these blocks, we can talk about the colour, and we can talk about the fact that, well, one block is floating, one block seems to be, pretty much in equilibrium, and one block appears to have sunk. These are all descriptions which we're giving, but we're not actually giving any kind of numerical values. Now, in terms of actually working out the density, on the other hand, we need to collect quantitative data, because density is going to be mass divided by volume, and of course we can only have the mass if we actually weigh each one of these cubes and therefore apply a numerical value to them, and we can only calculate the volume if we measure the dimensions of the cubes, and once again, as soon as we measure, we have numerical values and therefore we have quantitative data. And we'll simply do the mass of the cube divided by the volume of the cube to give us the density. And so what can we see here? Well, what we're actually seeing is we're seeing a comparison of different densities. Because remember, we have three different materials here, but these three different materials are sitting in water. So we are comparing the density of these three different blocks to the water in which they are contained. So if we look at this wood block, obviously we know the volume of these three blocks is going to be consistent. We can see they're pretty much all the same size. So the only difference therefore is going to be mass. And so it's rather unsurprising when you think about it. The wood is therefore going to have the lowest mass, the water is going to have an intermediate mass, and the stone block is obviously going to have the highest mass. Now, obviously because the block here is floating on the water, or in the water should I say, we therefore can assume with great certainty that the wood has a lower mass than a similar sized volume of water. In the case of the stone, we can therefore also assume that the stone has a higher mass than a similar sized body of water. Now, when it comes to a body of water, the cube here, we can see that it's floating right in the middle of our body of water. Essentially, it's in equilibrium with our water. And this is because the mass and the mass of a body of water, which is the same size as this cube here, is going to be the same. And so when the numbers are going to be the same, essentially it's going to be in equilibrium, it's going to be balanced. And that's why it's just happily floating, suspended in the water. It's not floating up and it's not sinking down. It's just sitting there right in the middle quite happily. So the next measurement we're going to think about is weight. So weight is defined as the downward force an object exerts under gravity, and it's dependent on two variables, the mass of the object in question and gravity. So when we look at this example here, we can see that we have the same person standing at two different locations, one on the Earth and one on the Moon. Now, obviously, because this is the same person, we know the person's mass, the person's volume, and therefore the person's density are going to be constant, so we don't have to worry about those. So this means the only variable with regard to weight in this model is going to be gravity. So we know, of course, that the Moon, as a smaller body of rock, will have weaker gravity than the Earth. So this means that when we weigh the person at these two different locations, we're actually going to find that the person will weigh less on the Moon because there is lower gravity. Now, this actually does have effects when it comes to geology. So one of the things that we have to think about is, why do mountains reach a certain height but not keep going up? Well, the thing about mountains is there's a certain point where the mountain essentially reaches its maximum possible height, at which point gravity, along with several other forces, is actively pulling the mountain range back down. And so this limits the height to which mountain ranges can get. In contrast, in lower gravity environments, let's say for instance somewhere like Mars, mountains can in theory be higher because gravity is weaker. And so the variation that we see in gravity and therefore its effect on weight will have geologic implications, for instance when it comes to the size, or more accurately the height, of geologic features such as mountain ranges. Okay everybody, thank you for watching this presentation and take care.